Welcome back again. This is Marlon Etcher from the Natural and Social Science Tutoring Lab here at Miami-Dade College Kendall campus, and this is the third video in the series of double replacement reactions. We're more than halfway home and figuring out how to solve these problems, and now we're going to look at the third and very important step in solving a double replacement reaction. So let's take a quick review of what we've done already. So in the beginning, we did step one, where we broke apart our initial compounds and we formed our product compounds. That's known as rearrangement, and you have to follow a certain set of rules according to that. Step two was crisscross your products, where you take the charges of your products, you crisscross them to find out if you have new subscripts which you must insert. In our particular example that we've been working on, the charges were opposite but equal, so the charges canceled each other and we did not have to change the subscripts. That's just in our particular case. Depending on your example, you may or may not have to change it. So make sure you do crisscross, because if you don't, you will not get the problem correct. Alright, so there was a few ideas and concepts associated with that as well. Now let's go ahead and look at the third step. The third step is known as solve for your product states, where you have to try and figure out if your products are soluble or insoluble in water. Because when you're reacting these two aqueous substances, we want to know if we're going to have a little particle emerge out of our solution, which would be called a precipitate, which we write as a little subscript of S for solid, and I'll show you that in a bit. But the idea is, how do we know if something's going to be soluble? Well, you're going to have to use what's known as the solubility chart. Now, the good thing about it is you don't have to memorize the solubility chart. In the majority of classes, you'll actually be provided with the chart. The particular chart that I took is from one of the textbooks, the modular books, so you'll be very familiar with it, and I think by using this it'll help you a lot during your exercises and examinations. Now, one of the very critical ideas, and a lot of students forget this, is this principle right here. A weak electrolyte must be formed, or else that reaction will not work, and the answer would simply be no reaction. Here in the tutoring lab, I get a lot of students that come to me and they ask me, why is this answer no reaction? I thought I did all the steps right. And then I realized that they forgot this very important principle, that if you don't form a weak electrolyte, then your answer should be no reaction. Of course, then the natural following question ensues is, what is a weak electrolyte? Well, here are a couple examples of weak electrolytes. There's the insoluble salt, which is a little parentheses S, which we'll talk about soon enough, according to the solubility rules. A weak acid or weak base. How do I know if I have a weak acid or weak base? Well, at this point, hopefully you started working on memorizing your list of strong acids and bases. Those are your strong acids. Everything else is weak. So you're not actually identifying these as weak acids. You're simply saying, oh, this is not a strong acid, then it must be a weak acid. So the way you can identify something as a weak acid or weak base is by memorizing the strong acids and bases, which you hopefully you're working on currently. Water formation, which you always get when you have an acid and a base react, you'll always form liquid water, which is listed as HOH or H2O. Hopefully you'll see one of those in the example. It's not too hard to see. Gas formation is a bit tricky. That can come up where you can actually produce carbon dioxide or SO2. Those are tricky questions, and hopefully when you run into those, you won't be too surprised that these are weak electrolytes. Anyways, going back to the topic, if you don't form one of these four weak electrolytes, then you actually have no reaction. So if we see one of these, it's actually a good thing, because that means our reaction will work. Let's go ahead and take a look at the next step. The solubility rules. And it seems very immense. I don't want you to take a look at it for too long right now. I just want you to realize that when we start trying to figure it out, we're going to come back to this table. But what we really just need to do is we just really need to figure out how to use the table. We don't have to memorize all the rules. We just simply have to learn how to use the table. So let's go ahead and look at our example and see where we were in our example. In our particular example, we had just finished crisscrossing and we realized that the charges were absolutely equal, so they canceled each other out. So this is the subscripts that are appropriate for my product compound. Now here I have sodium, and then here I have chlorate. So I need to find a rule that's either for the sodium, or I need to find a rule for chlorate that will tell me if this is going to be a soluble or insoluble compound. Notice that these are already given, but these are not. You have to solve for those. So let's go ahead and see if we can solve for that. So I go back to the solubility rules, And I find that right off the bat, it says all salts of alkali 1A, column 1A, are soluble. What did we had? We had sodium. Sodium is, if you were to look at the periodic table, is a 1A metal. So then that right there tells me that this guy, right off the bat, is soluble according to rule number 1. Also, for the chlorate, for the ClO3, the rule number 3 states that all salts containing the anions, meaning the negatively charged particle, ClO3, are soluble. So this compound is soluble according to rule 1 and rule 3. You don't actually need two rules. All you need is one. If you figure out one part, you have the whole thing figured out. But here we find it in two separate rules, and both of them say that this compound is soluble. So I'm going to come back here, and I have to remember what my little symbol is for soluble. For soluble, the symbol is AQ, which means aqueous, which means that this compound is soluble. Let's go ahead and go to our strontium sulfate, and let's try to figure out the state of that compound. Notice that we need a weak electrolyte. So far we don't have it. We don't have an insoluble salt. We have a soluble salt. So let's try to find a rule for either strontium or for the sulfate, and let's try to figure out if this is a soluble compound or not. So we come back, when you look at rule number 1, it talks about 1A metals being soluble. That's not going to help us here. We have strontium was a 2A metal. Ammonium salts are soluble. We don't have ammonium. Now here it says all salts containing the anions nitrate, chlorate, perchlorate, and acetate are soluble. Again, that doesn't quite help us. We don't have any of these negatively charged particles. If you recall, we had sulfate, which was SO4. Well, chlorine, bromine, and iodine are soluble except for silver, lead, and mercury salts. Nope, not going to help us. But look at here. Here it is. All SO4, otherwise known as sulfate, are soluble. And so a lot of students stop right here and they say, oh, soluble. But you have to read the entire statement. If you don't read the entire statement, you're going to get yourself into a lot of trouble, because it says all sulfates are soluble except for lead. And then here's our other piece, the strontium. And it says these guys are actually not soluble. So another way of interpreting this is that all sulfates are soluble except if you have lead, strontium, and barium. And we actually do have strontium. So in our particular case, it's an exception. And we have to come over here and we have to realize that most of the time sulfates make things soluble. But in our particular case, because of the strontium, this will become a solid, which we identify by putting a little s. That's the symbol for solid. So we figured out the states of these, and we've also seen that we have one weak electrolyte because we formed an insoluble salt. So that's great. This reaction will actually work. Let's go ahead and come over here and try to solve for our second example. In the first one, we have the first compound, we have iron phosphate. Let's see if we can find a rule for iron or if we can find a rule for phosphate. So if you come over again to your solubility chart, you see how important it is to recognize how to work with this. You start going through the list. I'm not going to read all of them to you. I want you to read through this and really start practicing with it. But basically, when you get all the way down to the bottom, you'd find the rule here for phosphates. And it says that all salts containing the anions, and phosphate being one of them, it says are insoluble, except for 1A metals and ammonium salts. We didn't have a 1A metal. We had iron, which was the transitional metal, and we don't have it attached to ammonium. So in this particular case, the phosphate makes this compound insoluble. So when you come over here, this particular guy here, this iron phosphate, is going to be insoluble. So we simply put a small little s on the subscript, and that specifies that this is an insoluble compound. Let's go ahead and look at the second one. Let's go ahead and look at our ammonium acetate. Let's try to find a rule for that. So for ammonium acetate, you could get it right off the bat from rule number 2. It says all ammonium salts are soluble. Notice there's no exception, so you could stop right there if you wanted to. But rule number 3 also gives you a hint. It says all salts containing the anions, and it gives you a couple. And then here's acetate, and it says they're soluble, and there's no exceptions listed for that as well. So according to rule 2 and 3, we can see that this particular compound here is also going to be soluble. So then over here, we would put AQ. And that's how you use the solubility rules. You go through it and you find a rule for one half of it, whether for the cation, the positively charged molecule, or for the anion. You find a rule for one of the two pieces that will help you figure out the state of your product. And hopefully you get at least one that's a weak electrolyte, or else you have no reaction. Try not to forget that rule, it's very important. In the next video, we'll just simply balance our reaction, which hopefully you've gotten pretty good at this point, and then we'll be actually done with this problem, so we're almost home. I hope this has been helpful, and I hope you're starting to see that it's not so bad when you're trying to do a double replacement reaction.